Alright, well, let's continue our talk with the coherence, which is the second shift in the Common Core standards. And again, I'm taking most of this from the publisher's criteria, which just has a wealth of information. And this is in particular coming from the K-8, but it says much the same thing in the one that includes the high school as well. So the idea of coherence, the shift of coherence, is that we want math to make sense across everything. That it's not just kind of this list of disconnected tricks or mnemonics to memorize everything, but it actually does make sense. It is coherent, and it's not only coherent as far as understandable, but it's coherent in the progression that it makes. And the connections that it makes together. So there are two types of coherence, really. There's vertical coherence, in which we're thinking across grade levels. How do things develop? How do ideas and concepts develop from one grade level to the next? And so, one great example of this is how to solve proportions. Proportions, when we first introduce them, usually kind of sixth and seventh grade year. Really, seventh grade has a lot of rate and proportion type problems. Is kind of the culmination of that. But if we're teaching how to solve proportions and we say that we should cross multiply and divide, we're really missing the point. That's a mnemonic. That's just something that you can easily remember and say. But there is no such thing as cross multiplication. It doesn't exist. And in fact, once you get into the higher grade levels, the only thing it does is confuse the issue, because if students get into rational expressions or rational functions, and they're trying to add these rational functions together or perform any operations with them, as soon as they see these fractions, they think they need to be cross multiplying and dividing. In fact, as soon as students hear cross multiply and divide, you can give them a simple problem like 1/3 plus 1/2, and they're going to cross multiply. But there is no such thing as cross multiplication. So instead, when we're teaching proportions, what would make coherent sense vertically would be to teach it with the idea of inverse operations. So that if you had x over 3 equals 7 over 8, the way to solve that is just to multiply both sides by 3, because that gets rid of the dividing by 3. The divide by 3 and the times by 3 become 1, which is the multiplicative identity, and so then we're left with just what x equals. So instead of cross multiply and divide, we think inverse operations, and that builds vertical coherence as we tie it higher up into the higher level mathematics once we get into 8th grade and high school level courses. Now there's also horizontal coherence, and this is making connections within the grade level. So looking at your own standards within your grade level, how do things connect to each other? The example that's in the publisher's criteria that they list is the bar graphs, and we shouldn't be teaching bar graphs kind of as a standalone topic. Instead, we can use the bar graphs and information on those bar graphs to help them continue learning how to solve basic arithmetic problems using the four operations. And so it's this opportunity to tie things together that makes sense. Another place for this would be, like, I'm an eighth grade teacher, so let me give an eighth grade example. The Pythagorean theorem and volume. These are not things that we would typically put together necessarily, but we could use the Pythagorean theorem to help us find the volume of cones. Let's say we can find the slant height there, or given the slant height, we can find the height of the cone if we have the radius of the cone. So that's a natural tie there together. Also, another one with Pythagorean theorem that we probably think of even less tying together is with transformational geometry. So with the Pythagorean theorem, you get Pythagorean triples that will work, like a 3, 4, 5 triangle or a 5, 12, 13. Well, any multiple of a triple is also a Pythagorean triple. So if a 3, 4, 5 is a Pythagorean triple, then a 6, 8, 10 is, because that's everything multiplied by 2 and everything multiplied by 3 in the same way. Well, those are just actually dilations. That's really just taking that triangle that originally worked as a right triangle, that we knew it's a right triangle, and the Pythagorean theorem, or Pythagorean formula rather, works with that. A squared plus b squared equals c squared. So if we dilate that triangle and make it larger, then it's still going to work, because we've just dilated it. It is similar. And so since it's a similar triangle, we're going to have the same properties going on as far as the proportionality of it. So really, that's a rich way to kind of make some of those connections. horizontally. And the more students can see those connections, the more likely they are to retain information and understand it. Because as they see something and can apply it in a new situation, in a new circumstance, then they're developing meaning of the mathematics that are there. All right, so some specific instructional implications for this coherence. We're going to probably need problems versus exercises. Now, we do need both, but a problem would be a situation where students actually don't know what to do, and these problems are going to make connections whenever possible within grade level. So instead of teaching it within isolation, again, we're making connections so that they have to transfer the knowledge from one area to another. An exercise is simply just, well, here's how you do it, plug and chug, spit it back out. That's just a straight regurgitation thing. But a problem, students are not going to know to begin with. At least they're going to have to figure something out. So oftentimes I'll give students something in class and they'll go, well, I don't know what to do, and I just tell them, good, you're not supposed to. If you already knew what to do, I wouldn't ask you this question. And so that's the type of thing a problem is, at least by the definition that we see in the publisher's criteria. Again, not to say we don't need exercises, that we're going to see that in a little bit, but the problems can help us build coherence. Also, it says explicitly in the publisher's criteria that we should be relating grade level concepts explicitly to prior knowledge. So we can say, hey, remember in 7th grade when you did blah blah blah, remember in 6th grade when you did blah blah blah, and bring those things up from year to year so that they see that. And a lot of times I'll even point ahead because that helps give students some context. So when we talk about long division, for example, just taught long division in class, again, when we're changing between versions of rational numbers. So we're changing a fraction into a repeating decimal, and they're remembering that long division process. And a lot of them are asking, well, why can't we just plug this into a calculator? And besides the fact that the Park blueprints say that we can't, the other argument is, well, coming up you're going to be doing some polynomial division, or it's possible that you could be doing some polynomial division. And so here's one relationship that's coming up ahead, or beyond this grade level. And so not only coherence from below, but also sometimes it's helpful to point them forward too, so they know where they're going. It gives them a little better vision of why they're taking the steps that they're taking. The publisher's criteria also says we should not be teaching micro standards. So if we take the standards that are there and we break them down into more little bitty standards, we're just going to be overwhelmed. And I completely agree with this. Unfortunately, I don't see a way around it. For example, again in the 8th grade, it says that we need to teach how to solve systems of equations. Well, if we're solving systems of equations, we're probably doing it by substitution, we're probably doing it by graphing, we're probably doing it by the elimination method. And even though it doesn't say the elimination method or the substitution method explicitly, those are probably things that I'm going to have to teach. So, but this may bump into some assessment issues too. So let me jump to those. The assessment issues then, if we were trying to teach, again, for example, the systems of equations, and it's not explicit as far as the substitution or the elimination method, we're still going to be teaching both of them, but when we assess, then to keep our coherence, to keep our focus, the students are going to be choosing which is the best method. So I'm not going to penalize them for using the substitution method when I think they should have used the elimination method. Or, that would just be my kind of personal preference for that problem. But the coherence will come when they can say, oh, look at how these two methods kind of connect and how I can pick and choose between them and which one makes sense in the context of this problem. So again, the focus and the coherence kind of relate together as far as our assessment. What are we really trying to get out of this? Also, if we're going to be coherent, again, nothing's going to be assessed for mastery that's out of grade level content. I'm not assessing previous standards. I'm not assessing coming up standards. I'm assessing my standards at my grade level to see how well students have mastered that. And that's, again, the coherent issue is that if I am correctly assessing my piece of the puzzle and everybody else's, then we've got one big coherent picture, rather than my picture of assessment kind of jumping all over the place and then we're not really sure what that means. That doesn't build coherence, that builds misunderstanding and not an accurate picture of what a student has actually mastered at that content. Also, one other kind of practical tip is this idea of interleaving. We've often been told that we should clump all the same problems together so that when we have a test or we have an assessment, we put all the ones where you turn the fractions into decimals right here, then all the ones where you turn repeating decimals into fractions next. Uh, and what research has shown us is that actually interleaving the problems, so by mixing them up, where students have to decide, oh, what do I actually do here, rather than figure out what the first one does and then just keep doing it by rote. If they're mixed up in how they're even listed on the paper, it helps students build that coherence because they're forced to think about how does this connect to the big picture, how does this connect to the essential questions of this unit. So interleaving is a good strategy, and it also, research has shown, even though it may be more frustrating for the students, it actually helps them learn better. So they retain that information longer, they understand it better. So that's another coherent issue, because again, if they're making those connections, it's not in isolation. It's not, here's this one skill. Okay, you've memorized this one skill, spit it back out, and then we're done. Instead, we mix up those questions and they show that they know how all these things connect. Okay, so I'm going to go to rigor next. You can join me there.